Alright, students, today we're going to be looking at exponential functions, doing sort of an introduction, and also talking about the graphs. And the questions that we're going to be looking at are, what is an exponential function? What does an exponential function look like? And finally, how does an exponential function compare to a polynomial function with respect to its growth? Alright, so what is an exponential function? Well, in a sort of informal way, an exponential function is any function that looks like this: y equals a times b to the x, where notice here the x is our independent variable and a and b are numbers or constants, if you will. An example would be like y equals 1 times 5 to the x. I'm going to use 1 here just for simplicity's sake. We'll see what happens if we change that number around here in a few minutes. So just plugging in some values here. That 1 essentially goes away. If I have negative 3, then we've got 5 to the negative third, which is, if you remember your exponent rules, 1 over 5 to the positive 3 power, which is 0.008. Negative 2 would be 5 to the negative 2 for the y value, so 1 over 5 squared, which is 0.04. If you got negative 1, that's 5 to the negative 1, so 1 over 5, which is 0.2. 0, we have 5 to the 0, which is 1. If we have x equals 1, then we have 5 to the first, which is 5, so we can see where this value is increasing very quickly. 2, 5 to the 2 is 25. 3, 5 cubed, 125. And if we go ahead and graph that, so our negative 3 was really close to the x-axis, negative 2, a little bit higher, negative 1, and then at x equals 0, we had a y value of 1. At x equals 1, we had a y value of 5, and then this one here, I put the dot there, it really should be way the heck up there, so I should have erased that dot, but that's okay. And if we draw this, it looks really steep here, and then it gets really close down here. Notice this graph never actually touches the x-axis. It gets closer and closer and closer and closer, but never actually touches it. So there's a horizontal asymptote right there. I'm not going to draw that on here, but that's something to note. If we go ahead and look at some graphs here, maybe look at a little bit more official version here, so y equals 1 times 5 to the x, you can see it gets close there but never hits it. And then we'll change that multiplier up in the front, that a value, to a 4. You can see that's this blue curve, and we are, I guess you could say, increasing faster. Also notice that the y-intercept there changed to 4. So that's a clue. We'll summarize this here in a bit, but that a value is the y-intercept. All right. What are some other things that we can do here? Well, let's see here. Let's change that base number to 10x. So instead of saying 1 times 5 to the x, we have 1 times 10 to the x. And you can see that's the green graph, and it is growing much faster. And if we zoom in, we can also see as it's sort of, if we're moving to the left, kind of looking at how it's decaying in this direction, it decays faster. So that multiplier there just increases the rate of growth, or increases the rate of decay. I shouldn't say a multiplier, I should say a base. Alright, what are some other things we could do? We could put a negative number out front here, and that's just going to make every positive value turn into a negative value. So here are our observations in sort of a summary form. So that a value is the y-intercept. The b value changes the growth or decay speed or rate. And there's other things here we'll talk about here in a minute if there's multipliers up here. If a is less than 0, so if a is negative, then all the y values are negative. And we saw that as well. All right. There's another different type of graph we want to look at here, and that's where we have a negative up here in the exponent location. So like 1 times 5 to the negative x. So kind of wrote this as 1.5, so I'm going to make it a little bit more obvious. 1 times 5 to the negative x. So negative 3 would be 5 to the negative 3. So that's 5 to the third, which would be 125. Negative 2 would be 5 to the negative 2, so 5 to the 2, or 5 to the second, 5 squared, so 25. Negative 1 would be 5 to the negative 1, so 5 to the first, which is 5. 0 is 5 to the negative 0, which is just 1. 1 would be 5 to the negative 1, so that's 1/5, 0.2. So we're kind of getting those same exact values that we saw a moment ago, when this was positive, but now those these higher values are on that negative side, and when we look at the graph, it's going to be real interesting here. So 2 turns into 5 to the negative 2, 1 over 5 squared, so that's 0.04, and then 3, 5 to the negative 3, so 0.008. And when we graph that, for negative 3, we get the 125. This is very rough here. Negative 2, we get the 25. Negative 1, we get the 5. At 0, we cross the y-axis there at 1, and then we go lower and lower. So this is called an exponential decay function. Those other ones were exponential growth. If we have a negative multiplier out front, then just like with the growth, everything which was positive now becomes negative. So it's exponential decay. So it's decaying because we would say the y values are approaching 0. They never actually hit 0, but they do approach 0. All right. So that's going to kind of lead us to this summary sort of slide here. There's 4 types of graphs that we've looked at when it comes to exponential. We've got positive growth, where it's going up. We have, I'd say, negative growth, where the growth is all in the negative y values, especially as we're kind of going here along the positive x direction. Positive decay, where the values are all positive, but they're decaying, and then you could have negative decay, which would be a graph something like that. Those are 4 types of exponential graphs. This top one, positive growth, y equals a times b to the x. Negative growth would be like a negative a times b to the x, and obvious. So just your function would have that sort of form. Positive decay would be a times b to the negative x. Mess up there. There we go. And negative decay would be something like y equals negative a times b to the negative x. Couple things to note here. In all these examples, I'm assuming that b is greater than 1. So like b would be 5 in our common example that we saw, maybe 2 or 7 or something along those lines. If perchance that base is between 0 and 1, then essentially what you have, like let's say it was like 1/2, it's 1/2 squared, which is 1/4, actually a smaller value. So situations which normally are growth turn into decay. Situations which are decay turn into growth. And I think we'll see that here in a moment. Also, exponential functions are used in science all over the place. This is one of the forms you might see where it's y equals a, normally like a capital A, times b to the kt. They'll use t rather than x, so t for the independent variable. And sometimes even you'll see versions, and there's more than just this, but just to kind of give you a little bit of an exposure to some of these ideas. They'll have t over tau. Well, so rather than having the multiplier out here out front, they put the multiplier as a divisor down here. But you could just as easily turn that, divided by tau to like multiplying by 1 over tau. So anyway, the whole idea is that you've got some number that's either multiplying or dividing that t value. So k or tau or whatever, they do affect the growth rate, and we can kind of see how that happens. And also you have y equals a times b to the negative kt. That's going to be like a generic decay function. And when we see that, we're normally only concerned with t-values that are greater than 0. And if that's the case, so t greater than or equal to 0, I should put that, then our y-intercept would be what the amount was at time t equals 0, or we could say our initial amount or our initial value. So that's the normal full function, but we normally are just concerned with that. So lots of phenomenon in natural sciences that deal with, even social sciences too, that deal with some sort of decay, and you get different k values there will affect whether it decays quickly or slowly or whatever. So here we have sort of showing the exponential decay, positive and negative. I'll kind of zoom in on that. And put a multiplier up there. Let's see here. Hold on. So here's the growth, exponential growth, and then I'm just going to change that multiplier there to a 2. You can see it rises faster. 3 rises even faster. 5, 6, so on and so forth. If I put it at numbers, this multiplier here is numbers, smaller than 1. So like if I put 1/2, you can imagine that as like, or it's 0.5, you can imagine that as like x divided by 2 or whatever. But so it gets a little bit wider as you have those values 0.1, 0.4. This is decay. Let's get things right. Negative 2x. Okay. So 5 to the negative x is our red line there. And then negative 2x, you can see, once again, it's decaying faster. At a faster rate. It's going to approach 0 much sooner. Here we have negative 7. It's kind of hard to see there because I decided to leave the cursor. Sorry about that. But you can see negative 7x there very quickly decaying. So. And then if I change those values to like a negative 0.9, it decays a little bit slower. I think I'll try 0.8, 0.7, 0.6. There we go. We can really see that it's going out there. And if you're ever concerned about which value you're really getting, you can just plug it into Desmos, kind of see what values you get. So we've talked about what is an exponential function. We've talked about what does an exponential function graph look like. And now to our final question, how does an exponential function compare to a polynomial function with respect to growth? Well, nothing like doing a few experiments here. So let's go ahead and go with our classic y equals 1 times 5 to the x, and we'll try x squared. See how those two combine. Now, we're really just looking at the growth portion, so I'm going to look at here my exponential versus my quadratic. And yeah, that exponential is growing much faster. What about x cubed? Okay, x cubed's getting a little bit better. A little bit closer there. 4, x fourth, all right. 5th. And they start to kind of overlap a little bit. It's kind of hard to differentiate between those two. X to the 6 looks like that one's kind of taken off a little bit. Now, in reality, we're not just concerned locally with what happens between like 0 and 2 and, from 0 to 3, but, over the long term, what does that growth look like? So here I have the exponential 1 times 5 to the x, and then down here, x to the 6, so a good old polynomial. And I've plugged in 200, and the exponential gives us 6.22 times 10 to the 139th power. And down here with our polynomial x to the 6, we have 6.4 times 10 to the 13th, I believe. So even though in this really sort of short range from 0, 1, and 2, it looks like maybe the x to the 6 might win. Over the long haul, man, that exponential function is explosive. I think I even tried some like 2000. Okay, yeah, it's out of the range here. The website 500, 400 there. Okay, into the exponential, it's going to be 3.87 times 10 to the 279th. Plug in that same value, that 400, down here to x to the 6, and I get 4.9 times 10 to the 15th. So vast significant difference over the long haul, and it's just going to get larger and larger, and that gap is going to increase. So the answer to our question here, which grows faster, exponential versus polynomial? Exponential all the way. In the short term, occasionally you get polynomials that win a little bit, but the exponential grows much faster. Always go for that exponential growth if you can get it. All right, thanks for watching.